Everywhere we look today, from smartphones to cars, homes to hospitals, we find remarkable computational power. Yet, the tiny engines driving this revolution often go unnoticed. We're talking about the microprocessor, a truly fundamental invention that changed our world. What exactly is a microprocessor, and how did this miniature marvel come to be? Join us as we journey through its fascinating history, uncovering the brilliance, challenges, and relentless innovation that brought us to where we are today. Before microprocessors, computers were colossal machines. Imagine rooms filled with thousands of glowing, heat-generating vacuum tubes, each acting as a switch. Early electronic computers, like ENIAC in the 1940s, were massive, expensive, and consumed enormous power. They could calculate, but their sheer size and frequent failures meant computing was far from accessible or practical. The dream was to make these powerful machines smaller, faster, and more reliable, sparking a quest for miniaturization. The first major breakthrough arrived in 1947 at Bell Labs with the invention of the transistor. Unlike bulky, fragile vacuum tubes, a transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. It's solid state, meaning no moving parts, much smaller, more reliable, and consumes far less power. Imagine replacing a light bulb with a tiny grain of sand that does the same job. This invention paved the way for a dramatic reduction in the size and cost of electronic devices, truly revolutionizing electronics. Even with transistors, computers still required hundreds, if not thousands, of individual components wired together. This led to complexity and manual assembly. The next leap came in 1958 with the invention of the integrated circuit, or IC, independently by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. An IC is a miniaturized electronic circuit with many components, like transistors, resistors, and capacitors, fabricated on a single piece of silicon. This innovation meant an entire circuit on one tiny chip, drastically reducing size, cost, and improving reliability. With transistors and integrated circuits mature, the stage was set for the microprocessor. In 1971, Intel, co-founded by Robert Noyce, introduced the Intel 4004, designed by Federico Faggin, Ted Hoff, and Stanley Mazur. The 4004 was the first commercially available single-chip microprocessor. Think, a full central processing unit, or CPU, the brain of a computer, etched onto a single small chip of silicon. Initially for a Japanese calculator, it was a 4-bit processor, processing data in chunks of 4 bits. It paved the way for personal computing as we know it. The 4004 ignited a relentless pursuit of miniaturization and power. This trend was famously predicted by Intel co-founder Gordon Moore in 1965. Moore's law observes that the number of transistors on an integrated circuit doubles approximately every 2 years. While not a physical law, it has served as a powerful self-fulfilling prophecy, driving engineers to constantly innovate. This exponential growth meant processors became incredibly more powerful and cheaper at an astonishing rate, fueling the rapid expansion of computing into every aspect of life. From the 4-bit Intel 4004, microprocessors quickly evolved. The 8-bit Intel 8080 fueled early personal computers, then came 16-bit chips, and by the 1990s, 32-bit processors were standard. Today, most general-purpose processors are 64-bit. This bit width refers to the amount of data a processor can handle at once, dramatically increasing processing power. This steady march from simpler designs to increasingly complex architectures, coupled with higher clock speeds, has allowed microprocessors to tackle ever more sophisticated tasks, from complex simulations to stunning graphics rendering. Today's microprocessors are marvels of engineering. We now have specialized processors like graphics processing units, or GPUs, optimized for visual tasks, and dedicated AI accelerators. Multi-core processors, essentially multiple brains on a single chip, allow parallel processing, handling many tasks simultaneously. These tiny powerhouses are not just in our computers, they manage complex car systems, enable life-saving medical devices, power vast data centers, and bring smart functionality to countless everyday objects. The microprocessor has truly transformed our world, weaving itself into modern society. What does the future hold for microprocessors? Traditional limits of silicon are being pushed, leading researchers to explore new frontiers. We're seeing exciting developments in quantum computing, which uses principles of quantum mechanics to solve problems intractable for classical computers. There's also intense research into neuromorphic chips, designed to mimic the human brain structure for highly efficient AI. Regardless of their form, increasing computational power while decreasing size and energy consumption will continue to drive innovation. The journey of the microprocessor is far from over, promising even more astounding advancements.